Page 10 of Properties of Curves. Number 9. The cubic polynomial here touches the line with equation y equals 9x plus 2 at the point 0, 2 and has a stationary point of -1, -7. Find, the ABC values of this function. So basically what we have is they give us the tangent line equation, but they don't really know what the polynomial equation is. So it's kind of a backwards problem, right? So we do know that this tangent line shares three things with the polynomial, right? It shares an x-coordinate, it shares a y-coordinate, and it shares a slope or a gradient. The x-coordinate and the y-coordinate are given right here. It's x1 is 0 and y1 is 2. The slope of the tangent line is 9 because this is already in slope-intercept form, so we can identify the number multiplied times x as the slope. Okay, so from these three numbers, 0, 2 for the x and the y coordinate, and the 9 slope, we should be able to figure out what a, b, c, d are. Okay, so first of all, let's find what the gradient function of p is, what the derivative of p is. So we'll find p dash. The way we do that is we use power rule. Okay, it's that. All right. And we know that this gradient at x equals 0 is going to be 9. So when x equals 0, p dash is equal to 9. So let's rewrite that. So 3a 0 squared plus 2b 0 plus c equals 9. So these two terms become 0 because they're multiplied times 0. So basically we found out that c is equal to 9. We can also figure out what d is. And this is not calculus. It's just they gave us a point 0, 2. If they give us the point 0, 2, we can plug in 0 into p. And then every single term, ax squared, bx squared, cx becomes 0 because we're going to plug 0 in for the x. And then we're left with d. And we know that the y coordinate at x equals 0 is 2. So we know that d is equal to 2. So now we have, let's see, the p function partially known. We know it's ax cubed plus bx squared plus 9x plus 2. We also know that the p function has a stationary point at -1, -7. This is also useful because we could use the derivative again. And now the derivative, we know it partially. We don't know what the a value is. We don't know what the b value is. But we don't know that the c value is 9, right? Well, we know that that has a stationary point at -1, -7. So we know that the derivative at x equals -1 is 0. So at x equals -1, we know that the derivative is 0. So let's plug those in and see if we can get more information. So 3a -1 squared plus 2b -1 plus 9 equals 0. So this gives us that 3a minus 2b plus 9 equals 0. And another thing we know is that -1 and -7 is a point on P. So if we put -1 and -7 here, we can find out that, let's see, -1 cubed, a -1 cubed plus b -1 squared plus 9 times -1 plus 2 is equal to -7. So that'll give us another equation with a and b in it, which will be -7 equals -a plus b And this would be minus 9 plus 2, so it would be minus 7. So we can add 7 to both sides, and then we'll have b minus a equals 0. So we know now that b is equal to a. If we know that b is equal to a, then this equation here becomes 3a minus 2a plus 9 equals 0. So a is equal to negative 9. And if a is equal to negative 9, then b is also equal to negative 9. So now we completely know the p function. We know that a is negative 9. We know that b is negative 9. We know that c is 9. And we know that d is 2. Okay, so that was kind of a long, complicated problem. Number 11, show that the function y is equal to 4e to the negative sine x has a local maximum when x equals pi over 4. So local maximums occur at stationary points. Stationary points occur when the derivative is 0. So let's find the derivative. Remember that this is a product of two functions. This would be the u, this would be the v. The u dash would equal to negative 4e to the negative x. The v dash is equal to cosine x. Y dash is equal to uv dash plus u dash v. So u is equal to 4e to the negative x. V dash is equal to cosine x. U dash is equal to negative 4e to the negative x. V is equal to sine x. And so this is a derivative, and we know that this derivative is equal to 0 at some point, and we're going to find out that it's going to be x equals pi over 4. But remember that for show that problem, you pretend you don't know what the x value is. Okay, so how do we find out that the x value is pi over 4 here? First of all, whenever you have a function equal to 0, you would like to make it into a multiplication, because then you'll be able to reduce it to something simpler where you can say, okay, either a has to be 0 or b equals 0. It's much simpler. How do you make it into a multiplication? By factoring out a common factor. The common factor here is 4e to the negative x, so let's factor that out. Cosine x minus sine x equals 0. Is 4e to the negative x ever equal to 0? No, because there's an asymptote at the horizontal line at 0. So the only thing that can equal 0 is cosine x minus sine x. That has to be 0. Cosine x equals sine x. Sine x divided by cosine x equals 1. So tangent of x equals 1. What are the angles which have a tangent of 1? It would be pi over 4 and other multiples of pi over 4, like 3/4 pi, etc. But so, yeah, this is one of the solutions. Okay, pi over 4. So we're done with that. Go to 13. Consider the function f of x equals x minus natural log of x. Show that the graph of y equals f of x has a local minimum and that this is the only turning point. Okay, so if we want to show that this graph has a local minimum, we want to find the derivative. The derivative is 1 minus 1 over x. We want to show that it's a local minimum, so we set the derivative equal to 0. We solve for x. X is equal to 1. So when x is equal to 1, there is there's a stationary point. Is there any other stationary point? No. Is it a local minimum? Well, to show that it's local minimum, we need to make a sign diagram and test the points to the right and to the left. If x equals 1, we have a station. Remember that since we have a natural log of x in the original problem, that means that the domain is any number greater than 0. So at 0, to the left of 0, we have no domain. So we do need to test the numbers to the right of 1 and the numbers between 0 and 1. If we test any big number to the right of 1, we know that this is going to be a very small number, so it'll be basically positive 1. If it is a number between 0 and 1, this number is going to become very big. It's going to become 1 minus a number bigger than 1, and then we'll get a negative. Okay, so now we've shown that this stationary point is a local minimum. And we know it's the only turning point because there's only one value, which makes f dash equal to 0. Hence prove that natural log of x is less than or equal to x minus 1 for all positive values of x. Let's sketch, based on this sign diagram of f dash, let's try to sketch the function f, okay? So I'm going to draw a little xy coordinate system. We know it doesn't exist over here. Basically, this function, we know it goes down, and then it has a minimum point at 1, and then it goes up, okay? And so this function, by the way, is f of x equals x minus natural log of x, right? What is the height of the minimum point? So if we plug 1 in to x minus natural log of x, it'll be 1 minus natural log of 1. Natural log of 1 is 0, so it's 1. So the coordinate of this minimum point is 1, 1. So basically, this function is always 1 or higher. So we could say that the function f of x, x minus natural log of x, in other words, is greater than or equal to 1, because it's always higher than the height 1. Now what we need to do is rearrange it a little bit. We can add natural log of x to both sides. We can subtract 1 from both sides. We would get x minus 1 is greater than or equal to natural log of x. And that's exactly what we wanted to prove. So we're done. Okay. Inflections and shape. Okay. So now we're going to kind of like explain what concavity means and what it means when the concavity is positive or negative. Okay, so if we look at this picture on the right side, do you notice that the slopes of these red tangent lines drawn along the quadratic of the parabola which opens down are going from left to right from a positive number, less positive, flat, negative, and bigger negative, right? So the evolution as we go from left to right is that the m value is getting smaller and smaller. The m value is becoming more and more negative, right? It goes from positive 2 to positive 1, positive 0, negative 1, negative 2. It is going, we're subtracting and subtracting more and more from it. It's getting smaller, okay? So for this parabola, we can see that it looks like it's concave downwards, right? Because concave down is when things are cupped down. The first derivative, we can see from 2, 1, 0, negative 1, this evolution, we can see that it's decreasing, okay? Which means that the rate of change of the slope is negative, right? The rate of change is like, how does it change going from 2 to 1, 1 to 0, 0 to negative 1? It's getting more negative, so it would be negative, okay? So this is why a cupped down shape has a negative second derivative and why it is concave down, okay? Because the slopes are steadily getting more negative. 2, 1, 0, negative 1, negative 2. And this picture is showing just the opposite. As we go left to right, and remember graphs, we'll read them left to right, the slope starts at negative 2 going down, less so, flat, starting to go up, going up more. So as we go left to right here, we can see that the slopes are getting more and more positive. What do we call this concavity? We call this concavity up because it opens up, it's cupped up. the slopes are steadily increasing, right? Because it transitions from -2 to -1 to 0, steadily increasing. And we know that the rate of change of the slopes is positive because the numbers are getting steadily more positive. Okay, so this is another demonstration that concave up is synonymous with a positive second derivative. Concave down is synonymous with a negative second derivative. Okay. A point of inflection is a point on the curve where there is a change of concavity. Okay, so if we have concave down and then we have concave up, the point that is in between the two is an inflection point. If we go the opposite way and we have concave up and then we have concave down, in between we have an inflection point. If the tangent at the point of inflection is blank, then this point is stationary horizontal inflection point. So if the tangent at the point of inflection is horizontal, then this point is a stationary or horizontal inflection point. These two drawings here are horizontal stationary inflection points. Okay. In a non-horizontal or a non-stationary inflection point, and I've drawn two examples here, these are non-stationary inflection points. You can see that the tangent line that goes through the inflection points are not horizontal, they're diagonal. The tangent line crosses the curve at this point. So yeah, of course the tangent line crosses the curve at the inflection point. I wrote something that's kind of misleading here because notice that in every single case, even the horizontal cases, the tangent line crosses the curve at the inflection point and it goes through the curve, you see, because normally tangent lines, we're used to just seeing them kind of hug the surface of the curve and it doesn't actually cross it. But you can see here that when you have an inflection point, it actually crosses the curve. That's it.